Alright, welcome back. We've learned that it's bad news about climate, right? It doesn't matter how rosy our future... Well, it does matter how rosy or how pessimistic our view of the future is with regard to population, affluence, energy intensity, or carbon intensity. No matter what, the amount of carbon dioxide in the atmosphere is increasing. But it does depend greatly on what the future is like. Do we have a global economy or not? Is population peaking, or is population just growing exponentially, and so on? We now have a range of possible carbon dioxide concentrations from which we can get a range of radiative forcings. Now again, remember this notation of A1, A2, B2, and B2 has sort of fallen out of fashion a little bit in recent years. We're going to see that there's actually a way that we can talk about this directly in terms of radiative forcing, which is kind of the more en vogue way of doing it now. But in the meantime, you can kind of picture what's going to happen here. We're going to be using these greenhouse gas emissions that interdisciplinary teams of scientists have defined as possible scenarios for the future. We're going to use those as boundary conditions for our model. We're going to feed it to some big old rack of a supercomputer someplace and tell it to chew on that, making a forecast based on the 7 primitive equations. It's going to run a numerical model of the climate out for the next 100 years, or further for that matter. And we start getting these diagrams here that give us senses of like what the global climate is going to be, global mean temperature is going to be for the rest of the 21st century. Now, I want you to notice, by the way, on here, on these diagrams, for whatever reason they kind of changed how they're doing this. Instead of defining the temperature change as being since the Industrial Revolution, we're now defining it as being since the year 2000. So, like, if they say there's been a 1 degree warming, they mean since the year 2000. So that's on top of the roughly 1 degree of warming we've had up to the year 2000. Alright, so you can see for a variety of different scenarios for the future, we have the curve showing the global mean temperature. You can see over there on the right-hand side of the diagram here, we actually can see how ensembles of these models have been used to create different scenarios for the future to get a sense of the range of the different warming. And what I want you to notice is the pink curve is something different. The pink curve is if like we stopped emitting carbon dioxide altogether. So for the range of different solutions we see here, you can see that by the year 2100 we have a range of warming. We ran an ensemble of different models with an ensemble of different boundary conditions, and we get a range of possible outcomes, and we see that by the year 2100 the world will warm an additional 1.8 to an additional 3.6 degrees Celsius. That's over and above the warming we've already seen. Oh my, that's a whole lot of warming. What I also want to draw your attention to here, see that pink curve down there? That's if we have no more addition of carbon dioxide in the atmosphere. That's the committed warming, right? That is the warming that will happen if we just let the Earth come to radiative balanced thermal equilibrium with the greenhouse gases that are already in the atmosphere. You can see we have another ½ degree of warming or something to go. But we talked about that in the second module of the course. Notice then for each of the scenarios, like I have circled there B1, what happened is groups like the IPCC and AMIP have coordinated to have a large number of climate research groups run their model using the B1 boundary conditions. And we see then, based on different models and their different assumptions and their different solutions to the 7 primitive equations, they do get slightly or not so slightly different futures. And so like in B1, you can see that the most optimistic model shows only a little over 1 degree of warming after the year 2000, and the least optimistic shows as much as almost 3 degrees of warming by the year 2000. By the year 2100. So you get a range. That's what those error bars there are showing. Notice we're not using something like a spaghetti diagram here. We're just using error bars on the forecast now to show the range that the ensemble is giving us. So the ensemble models give us a way of seeing this range of possible outcomes. And you can see that some of those outcomes are bad. No, all of those outcomes are bad. And that takes us just out to the year 2100. What about beyond the year 2100? I mean, we don't try to make A1, A2, B1, B2 type scenarios out farther than that, because beyond the year 2100, it's not entirely clear that we can make meaningful predictions about what the economy is going to be like, what the demography is going to be like, societal and technological changes beyond that point. That's not really something science gives us. But that doesn't change the fact that, God willing, and the river don't rise, there will be people. There might be you. Right? I'm not planning on seeing the year 2100 because I'd be 130 years old. But you might be there. My kids will be there. My grandkids will be there. There'll be people there. And those people are going to wish that we had planned about their lives. They're going to wish that we had thought through what the consequences of our decisions are going to be for their world. So we need to at least be able to think about what their world is going to be. All right. For example, in the year 2100, are we going to be using fossil fuels? Maybe. That depends. In a lot of the scenarios that we worked on, A1, B1, A2, B2, on a lot of them we were still using, in fact, a lot of fossil fuels in the year 2100. By the way, this is the Google image search on futuristic oil drilling platform. I liked that diagram very much. I'd like to think that by the year 2100 we are no longer using fossil fuels and we have wonderful green technologies using nuclear fusion or space-based solar arrays or God knows what. But I don't know. And neither does really anybody else. I mean, it's certainly presumed that at some point we're going to hit something like peak oil. Now, this idea of peak oil is a tricky concept that gets used lots of different ways, but peak oil is basically this idea that there's some point in the future at which it no longer makes economic sense. Well, we will have reached the peak of the amount of carbon that we are extracting from the lithosphere, the rock of the earth, and instead we are finding other solutions just because it becomes too expensive to keep getting carbon out of the atmosphere, out of the ground. Well, we would like to think that, well, from a climate point of view anyway, we would like to think that we'll hit peak oil at some point, and that point is not so far away, so that we would stop using coal, stop using natural gas, stop using oil, and switch to something green and cheap and all that kind of good stuff. But so far that's not been the case. So far it's been the case that sources of carbon that used to be considered economically impossible are something that we use. The classic example is kind of just tar sands. It isn't like we just discovered the tar sands. They've known they're there. The problem was the technology didn't exist to recover the tar sands, get the petroleum out of it in an economically useful way. Now we can. Same with fracking. Fracking isn't such a wild and wonderful invention. It's just that the technology to do it in a cost-effective way to get to that natural gas and those shale oils and so on didn't exist. Now it does. So far, anyway, it looks like we are just going to keep using technology to find more fossil fuels rather than using technology to find emissions-free sources of energy. That doesn't speak very well for the future. But no matter what, no matter whether we emit, whether the future comes soon and we quickly get off of fossil fuels, or whether it happens a really long time in the future, at some point, we got to get this carbon out of the atmosphere. And it turns out it takes a really long time for the natural carbon cycle to remove the carbon dioxide from the atmosphere. And for that purposes, I'm actually going to use some figures that come from this journal article that I cite over there, Irreversible Climate Change Due to Carbon Dioxide Emissions. Nice classic paper on the business of getting carbon out of the atmosphere in the distant future. And I want to highlight how these diagrams are working here. So they're going way far out into the future here. Notice on the x-axis, we go all the way out to the year 3000. And what they're doing here on this first diagram here is the y-axis is just the amount of carbon dioxide in the atmosphere measured in parts per million. And what they are running here is a variety of different scenarios where, like, for example, in the one I have highlighted here in red, they're saying, what if we get as far as having a concentration in the atmosphere of 450 parts per million, and then we've hit peak oil, or we've discovered nuclear fusion or whatever, and we don't emit anymore. Well, at first carbon dioxide concentrations in the atmosphere will fall relatively quickly, but then they sort of start falling much more slowly. And in fact, even by the year 3000, 1,000 years into the future, we still aren't even back to the pre-industrial levels. See, the concentrations fall relatively fast at first because there's a relatively large gradient between the amount of carbon dioxide in the atmosphere and the amount in the surface ocean. The mixed layer, as we called it back when we talked about the carbon cycle. But so when we stop adding carbon dioxide to the atmosphere, at first that relatively large gradient between the atmosphere and the ocean drives carbon into the ocean relatively quickly. But as that concentration falls in the atmosphere, that gradient gets smaller and smaller, and in fact the rate at which carbon dioxide is moved from the atmosphere into the ocean becomes very small. And you get stuck for a very long period of time with this relatively high carbon dioxide concentration. And look how horrible it is if we let the carbon dioxide concentration get to, say, 850 parts per million. Remember, at the present time, we're at about 400 parts per million. If we don't get off of fossil fuels until the carbon dioxide concentration hits 850 parts per million, look at how high the carbon, 1,000 years into the future, the carbon dioxide concentrations are still around 550 parts per million. Think of the radiative forcing associated with a carbon dioxide concentration of 550 parts per million. We're not going to like the climate. Well, we're not going to be there. Your descendants are not going to like the world that has a carbon dioxide concentration that high for that long. I mean, look at how very high, I've just kind of indicated the area under the curve there with the red. All that time is a positive radiative forcing on the climate. That is a planet that is very warm for a very long period of time. Oh, so what does that actually mean then for like global average temperature? All right, so here they're using, again, the y-axis here is surface warming in Kelvin, and we have a x-axis that extends all the way out to the year 3000. And you can see that if we have the insanely optimistic possibility of the carbon dioxide concentrations never get higher than 450, again, we currently have 400 parts per million, well, even 1,000 years from now into the future, the planet is still a degree warmer than it was at the start of the Industrial Revolution. I mean, this is a very long period of time that our descendants are paying the price for how we are using fossil fuels. In fact, if you let it go all the way to 850 parts per million before we get off of fossil fuels, you can see that your distant descendants will have to deal with about 3 degrees Celsius of global warming. 1,000 years from now. This is a very serious problem. In fact, this is where we're going to see the word irreversible come in. I thought it was on the next slide, but we're going to see a few things first. Just to give an example of how bad of a climate situation this is, for example, this diagram here is thermal expansion of the ocean. Now, this is not like as in melting Antarctica and stuff. This is just literally as the ocean gets warmer, as the water expands. And you can see that, for example, if we let the carbon dioxide concentrations get as high as 850 parts per million, which is certainly likely in some of the worst, A1FI type scenarios that we talked about before, 1,000 years from now, we're still dealing with a meter of sea level rise. 1,000 years in the future, the water is still a meter higher than it is now, than it was pre-industrially, and that's just due to thermal expansion. That's not including things like melting ice sheets and stuff like that, which are difficult to model. That's not included in this factor here. Oh my gosh. So, regardless of how high we let carbon dioxide emissions, how high we let carbon dioxide concentrations get, whether we are peaking at 450, 550, 650, or 850 parts per million, no matter what, the consequences for the distant future are surprisingly large. The associated warming doesn't go away when we solve this when we get off of fossil fuels. The associated warming goes on for centuries. This is where we get this term irreversible climate change. In climate science, we describe the global warming caused by carbon dioxide emissions as being irreversible. We can't, it's not irreversible in the literal sense of the word, like it can't be undone, but it takes on the order of like hundreds of thousands of years for the carbon cycle to get that carbon dioxide out of the atmosphere. That's in contrast to a more reversible climate change, like say associated with a volcanic eruption. Well, the sulfate aerosols that are added to the atmosphere by the volcanic eruption cause a very large climate forcing, a radiative forcing, but they are easily scrubbed from the atmosphere by precipitation and so on. It is relatively easy to reverse that climate change. This is an irreversible climate change. We can't get this out of there unless we can actually remove the carbon dioxide, which we've talked about before is not a simple possibility. Oh man, the future looks terrible in all these scenarios. We're going to have to start seeing what more we can learn about the different future scenarios of the climate. But in the meantime, let's answer a couple quick more questions. Question 6. Okay, so I'm taking one of the figures from that paper that we talked about before. On these graphs, they show carbon dioxide concentrations in the atmosphere for the next 1,000 years. And in the red curve, I've highlighted the one where it shows the concentration of carbon dioxide peaking around 850 parts per million. Why does the carbon dioxide concentration just slowly fall for the next 800 years or so in that simulation? A, the plot is assumed, so why is it falling and why is it falling slowly? A, the plot is assuming that the natural carbon cycle will slowly transfer carbon dioxide from the atmosphere into other reservoirs of carbon. B, the plot is assuming that humanity will be able to make technological solutions to remove carbon dioxide from the atmosphere by that time. Or C, the plot assumes that there's only so much carbon dioxide that the atmosphere can hold, and after that it becomes saturated with carbon dioxide, and the excess carbon dioxide is removed by precipitation and evaporation. Okay, that question gets a bit wordy. Read it carefully and answer. Make a choice from those three options before you move on.